So let's take a look here at covalent compounds. We're going to be looking at the VSEPR theory, going into dot structures and everything. Let's see here. Learning targets. Molecular compounds are arranged based on Lewis diagrams, valence shell electron pair repulsion theory. That's the overarching understanding. So a couple of things. You're going to be able to draw the Lewis dot diagram, or that's the main learning target for 2.5. All right, 2.6, we're going to go in a little bit more depth. Resonance is taught in Chem 1, but formal charge is not, so this is just one little added thing on top. It's not particularly difficult, but it is an added feature for AP. So you're going to represent the molecule with the Lewis diagram using formal charges. You're also going to be able to draw ones that have odd numbers of electrons, because there's a few exceptions out there. And recognize Lewis diagrams that show resonance. And also draw them so that you represent the resonance correctly. And then there's 2.7, which is more about the shapes. Hybridization. So define VSEPR theory. Predict the following molecules and polyatomic ions. Their geometry. Bond angles. Relative bond lengths and bond energies based on bond order. Polarity, of course, with dipole moments. Orbital hybridization for both the sigma and pi bonds. Determine which bonds can rotate. So those are all what we're going to encompass in this set of notes. And they all kind of work together, so that's why I put them all together in this one big grouping of notes. Now, the shape of a molecule plays an important role in its reactivity. So that's, of course, why we're looking at this. Why do we care about? By noting the number of bonding and non-bonding electron pairs, we can easily predict the shape of the molecule. So bonding pairs, of course, are between atoms, like so. This would be a bonding pair, it's shared. The lone pairs that we put on the Lewis dot diagrams, we usually use the 2 dots kind of structure there. The lone pairs are what we would call the non-bonding pairs, okay? So referring to lone pairs and non-bonding pairs, you know, that will go back and forth, and they mean the same thing. All right. Simply put, electron pairs, whether they are bonding or non-bonding, are going to repel each other. We already know this. Electrons are negatively charged particles, so they're going to repel other negatively charged particles. Assuming the electron pairs are placed as far apart as possible from each other, we can predict the shape of the molecule. All right. Now, electron domains. A bonded pair or a non-bonded pair, a lone pair, they are all known as electron domains. And we're focusing around the central atom when we're talking about the electron domains. Okay, so here is our central atom A for this particular drawing. It has 3 ligands. The outside atoms are called ligands, and they're all B, like so. But if you look at the diagram there, should be able to count the electron domains around the central atom. And note, if you have a double or triple bond, like so, we have a double bond here. This one in particular, you know, shows the double bond, but that it still only counts as one electron domain, okay? So they are shared in the same area around the central atom, so that whether it's a double or triple bond, it only counts as one electron domain. So if we're looking at our particular diagram here, central atom in this molecule A has 4 electron domains. Okay, we have 1, 2, 3 bonded domains and 1 lone pair or non-bonded domain. So this is a total of 4 around this particular diagram. All right, valence shell electron pair repulsion theory. As you can see, this is why we abbreviate it and call it VSEPR. VSEPR theory. The best arrangement of a given number of electron domains is the one that minimizes repulsion among them. So that is, of course, they try to spread themselves out around the central atom. So lone pairs and bonded pairs are spaced out as far apart from one another as they can get, minimizing those repulsions. Good so far? All right. Seems like review of last year, pretty good? Yes, no, maybe not? Okay. Well, hopefully you will have one of these out in front of you. I know there's going to be one in your textbook. This should be in chapter 11 of our e-text. But you can find these on Google under images. All you have to do is type in electron domain geometries, and a bunch of them will pop up, various versions. But this basically shows you the different groups of the electron domains, okay? So you have 5 different types that are going to drive the shape. You have one that has 2 domains, 3 domains, 4 domains, 5 domains, or 6 domains around the central atom. And we're going to go step by step. We're going to start with the 2 domains, which is the linear electron domain. Then we'll move on to the next one that has 3, which is the trigonal planar, and so forth. We're going to do it step by step through this. So we'll build on starting with the easier structures and move on to the more challenging structures. But as you can see, under each domain, you have I always start with the one where it's all bonded. So here we have a linear molecule where you have 2 bonded atoms to the central atom, okay? And basically, you only have the one shape in there. It's going to be linear, okay? Under the trigonal planar, you have the 3 domains. 3 domains around the central atom, but there's 2 possible shapes. There's the one with all bonded atoms, and then there's the one that has 2 bonded atoms and a lone pair. So you have bent versus the trigonal planar shape, but they're both under the trigonal planar domain because they have 3 electron domains around them. And eventually, like I said, we'll build up over here, getting to our octahedral, which has 6. So there's like 1, 2, 3, 4, 5, 6 domains around the central atom. And if it's all bonded, all of them are bonded atoms like in this one, it is the octahedral shape. But if you take off 1 and you have 5 bonded atoms with a lone pair, it turns into a square pyramidal shape. You take off 2, so this would be 1, 2, 3, 4 bonded atoms, 2 lone pairs. Now you've got the square planar shape. So the domains really kind of drive, eventually becomes a pattern as to how the shapes come about. From the shapes, we're also going to look at the bond angles, we're going to look at the hybridization, and the polarity. So lots of different things that we're going to work off of, and then we'll have this nice big summary, diagram that you can use, especially when you're trying to do your problem set. This is a good diagram to have out. Okay, electron domain geometries. All one must do is count the number of domains in the Lewis dot structure. The geometry that by which corresponds to the number of domains. Okay, so here this has 1 lone pair, and then we have 3 bonded atoms. So this one has 4 domains, and it falls under the tetrahedral domain. Tetrahedral domain, though, is not its shape. Its shape is actually the pyramidal, because it has 3 bonded atoms in 1 lone pair. And that pushes the hydrogens down and it makes it sort of like a mini pyramid. Like I said, we'll have lots of practice with this. And we'll, as we're drawing them, we'll be looking at their ball and stick models and being able to tell kind of the 3D version of each one. All right, electron domain geometry is often not the shape of the molecule, just like we saw here with the ammonia. It's in the tetrahedral domain because it has 4 domains, but it is the pyramidal shape, the T-pyramidal shape, because it has 1 lone pair, pushes the other 3 atoms downward, and therefore we're going to have a little bit more of a pyramid shape rather than an equally spaced tetrahedral shape. All right, so within each electron domain, there might be more than 1 geometry. In the tetrahedral, we have tetrahedral shape, the trigonal, pyramidal, and the bent shape. So there's 3 different shapes under that domain. And like I said, we're going to build on each one. What you should notice about what changes the shape a little bit too is the lone pair. Like this one has the lone pair on the top here. And that lone pair actually takes up a little bit more space than a bonded pair. So it pushes the other 3 atoms down. This one has 2 lone pairs off of it, which further pushes the 2 atoms, these guys, closer together a little bit, so that affects the bond angle. And we'll talk about that too when we get to the bond angles. All right, valence bond theory. Hybridization. Major player in the approach to bonding. There are 2 ways orbitals can overlap to form bonds between atoms. Our first one are called sigma bonds. Sigma bonds, of course, we have this lowercase Greek letter. A little bit different than the lowercase delta that we use for partial charges. Just has the line that goes across the top. Sigma bonds are characterized by head-to-head overlap of S and P orbitals. So you have your internuclear, like here's the nucleus, and you have the overlap here of the S and P orbitals forming a sigma bond. Now sigma bonds form all single bonds. Anything that only has a single bond, the type of bond it has is a sigma bond because it's an SP overlap. Whereas the pi bonds are slightly different. The pi bonds we'll take a look at are a P to P overlap on a different plane. Okay, the P to P overlap, side to side overlap of the P orbitals, and it kind of forms this cloud, as you can see, because if you remember, P orbitals are supposed to be dumbbell shaped, right? So if they were separated and they weren't overlapping, we would see the 2 separate P orbitals. They have the one lobe that goes up, the one lobe that goes down. And remember, there's 3 of these on the different planes, the X, Y, and Z plane. But when the P and P overlap here, you see this kind of pink cloud, that's where the double or triple bond's going to be. So if a particular bond between 2 atoms is a double, you have 1 sigma bond, and then you're going to have 1 pi bond. So one where the S and P overlap, and then one where the additional P orbitals overlap. And if you have a triple bond, you're going to have 1 sigma and then 2 pi bonds. And the P's are going to overlap on different planes. And there's a nice diagram coming up here on the next slide to show you. All right, so once again, if it's just a single bond, like here the H2 single bond, you're only going to have a sigma bond. This one is ethene. Got 2 carbons, but we have a double bond in there, so it's going to be an alkene. In that, you have 1 sigma and 1 pi. So one of them's a sigma, one of them's a pi. And then here on our nitrogen, our diatomic nitrogen, we have a triple. Okay, 1, 2, 3. 1 sigma and 2 pi bonds in that triple bond for nitrogen. This was the picture I was referring to where it's showing you the overlap. The purple in the middle, the purple is showing you the sp overlap for the sigma bond. Okay? So 2 sp orbitals, sigma bond here, that's going to be this purple. All right? Now this is representing, let's see here, what are we got here? We got C2H2 is the molecule. 2 carbons, 2 hydrogens, and that's going to be ethine. If you remember your organic, ethine, YNE for the triple bond ones. All right, so there is our sigma bond up there. Now, you can see the 2 pairs of p orbitals are overlapping to create the 2 pi bonds. One of the pi bonds is like this, and it's like, if you're looking at it this way, that would be considered like the, what? The y plane, I guess. And then the other one goes forward and goes backwards. So it's on the other plane. And that's what's creating the triple bond. And as you can see, by adding in those pi bonds, that's also why the length shortens. Okay, pulls the atoms in closer together. All right. Now we're going to start looking at our lovely domains and start drawing, adding in angles and shapes and hybridization and all that good stuff. So, number of domains, 2 here, okay, and they're going to be bonded, okay, 2 bonded atoms, no lone pairs in this particular one, and one example would be like carbon dioxide here. And we're actually going to draw the carbon dioxide and check that out and see that. So only one molecular geometry under this domain, which is linear. So the only shape you'll find under that one is linear. And if you only have 2 atoms, you know, like something like HF, okay, or, you know, Cl2, something like that, where there's only 2 atoms in it, obviously only you have is a point A and a point B, and it's going to form a straight line. Okay? All right, so how do the hybrids work in the linear domain? Mixing S and P orbitals yields 2 degenerate orbitals that are hybrids of the 2 orbitals. Now, once again, why do they hybridize? It is to form a lower energy state for the electrons that are going to be there. And where do these hybrids occur? They occur around the central atom. Okay? So, sp hybrid orbitals have 2 lobes like a p orbital. One of the lobes is larger and more rounded as the s. So really, think of the hybrids. They're at a little bit lower energy state, but it is like we've got our round spherical S, blue here, our not so big dumbbell P in the red over here, and they're going to make purple. Red and blue make purple. But as you see, the purple is a little bit wider on the lobes because of that spherical shape from the S, makes it a little bit wider. So really, that's basically all we're doing is blending the 2 orbitals into another. Looks like a p orbital, however, it's just slightly bigger in the lobes, and it puts it at a lower energy state. So why would it do this? Well, it puts it at a lower energy state. Okay? And you're going to have 2, 1, 2, 1 for each side of the central atom that's being bonded. So this particular case, you only have to merge 2 orbitals because you only are going to have 2 bonded regions around the central atom. All right, so here's showing you a nice example. The degenerate orbitals align themselves so that they're 180 degrees away. Once again, the purpose of that is to spread out the electrons as far apart from one another as possible. It's consistent with the observed geometry, okay? And here, linear, the overlap region As you can see, the hybrid orbitals are around the central atom here, beryllium. That's why they're purple. And the F's are contributing their p orbitals to the mix in order to form the bond. So we see, yeah, the 2p orbital from fluorine, that's where its valence electron is going to be, and the overlap region here for beryllium. Now, I did tell you before that beryllium is kind of different and behaves differently than other ones. It is a metal, but it does covalent bonding. So beryllium fluoride here is going to be considered a covalent compound or a molecule. And the beryllium, as you'll notice on your Lewis dot structures rules list, I put the exceptions there and other things to remember at the bottom of the page. But beryllium, in order to have a satisfied octet or a stable configuration, only needs 4 valence electrons in order to reach that stability. Before we get into drawing, I just want to pull up and remember the dipole moment idea, because we're going to be drawing them in, and we're going to be using that to figure out polarity. So remember, the dipole moments always point towards the most electronegative element, and if the dipole moments cancel out, it's going to be nonpolar. If they cancel, if they don't cancel, of course, you have a directional dipole moment where, like for instance here in this one, partial negative, partial positive. You have 2 ends to the molecule, then it's considered polar. All right, let's start with drawing carbon dioxide. So taking a look here, now we want to go back to our rules. What is the first thing it tells us to do on our rules? Always count the valence electrons. Very good. Okay, so we have C. How many valence electrons for C? 4. Good. How many for oxygen? 6. But we have 2, so we have to multiply that by 2, because there's 2 in our formula here, so that's 12. So 4 plus the 12 gives us a total of 16 valence electrons to work with. Always count your electrons. What does the second rule say? You have to decide on the central atom. Central atom cannot be hydrogen. Not that there's hydrogen in this one. It's usually the first one in the formula, because the first one in the formula is usually the least electronegative element. So out of carbon and oxygen, we know that carbon is definitely less electronegative. Oxygen's number 2 on the electronegativity, right? Only second to fluorine. So carbon definitely goes in the center. So we put carbon in the center. Then we have to attach the ligands. How do we attach the ligands? By single bonds. And our 2 ligands in this case are going to be oxygen. Those are going to be the outside atoms. So draw them, attach them by single bonds. How many electrons have I used so far in my drawing? 4. So I need to take away 4, and I end up now, I have 12 left over. What's the next thing on the rule list? What do we need to do? Satisfy the octets of the ligands. So we're going to satisfy the octets of our oxygen first. So this one needs 6, right? Because now it has 2, 4, 6, 8, right? Around it. Follow me there so far? So this one also would be 2, 4, 6. But that means now we're down to 0 electrons. I'm going to redraw this slide real quick, just so the checks don't get in the way. We ran out of electrons. We have a problem here. Which particular atom does not have the octet that it needs? Carbon. Carbon does not. When you run out of electrons, that tells you immediately that you're going to either have to do a double or a triple bond in order to satisfy the octet. Now here, we can take an electron pair off of the oxygen to form the double bond, like so. All right. That's good. Now the carbon has 6. So what else do we need to do? We need to remove another one of the lone pairs and create a double bond. Now I'm going to show you that we're going to do it from this side, and it really doesn't matter which one you take. It really doesn't matter. Okay, like so. The reason why I did that instead of doing something like this ultimately has to do with formal charge, even though you don't know how to calculate it yet. But I kind of wrote those rules down at the bottom, things to remember when drawing dot structures. Hydrogen always needs 2, that's important. Carbon, nitrogen, oxygen, fluorine will always follow the octet rule. They do not deviate from the octet rule. That means they have 8 electrons, or they must have 8 electrons. General bonding trends when they are around central atoms or even ligands to carbon groups typically form 4 bonds and no lone pairs. So that's talking like carbon, silicon, germanium. Okay? The metalloids can do covalent bonding, so they would count. Nitrogen group is going to form 3 bonds with 1 lone pair. Typically that's the case. And then the oxygen group is typically going to form 2 bonds with only 2 lone pairs. There will be an occasion when we might have this arrangement of the 1 bond with 3 lone pairs, but that happens more in the polyatomic ions, not in our regular molecular. So I want you to follow this rule when you're doing the regular molecular, that generally oxygen should have 2 bonds and 2 lone pairs. That is going to fit the formal charge rules better. Like I said, unless you're drawing a polyatomic, which I will show you, that's where some of this starts to deviate a little bit. So this would not be an appropriate structure for carbon dioxide, and we wouldn't want to draw it that way, because we want to make sure that oxygen has 2 bonds, 2 lone pairs, when we're not drawing polyatomic ions. So now we need to list out the hybridization. Okay, so, and when we're listing out hybridization, we want to list out also the number of bonds. Okay, so what is the first bond here between our carbon and our oxygen? What type of bond is it? Well, it is a double bond, but within the double bond, there are 2 types of bonds in there. We have a sigma bond. What kind of sigma bond? What is the hybrid of the sigma? How many orbitals merged in order to form the hybrid for the linear domain? 2. So this is going to be, we're going to have this one. That's going to be 2 sp sigma bonds. Okay? Sp hybrids, remember 2 orbitals are going to merge to form the hybrid around the carbon. So we have 2 sp sigma bonds. And then what about these other 2 bonds? What are these going to be? These are going to be, so we have 2 pi bonds. What's the bond angle going to be? Between, it's O to C to O bond angle. And it's a straight line, so we know this is going to be 180, right? 180 degrees. And the last thing we need to look at is the polarity, because we already know this is under the linear shape. How do the dipole moments go? Which way do they point? Towards the oxygen or towards the carbon? They point away towards the oxygens because it's more electronegative, like so, right? And we would say the dipole moments do what here? They cancel. So this overall molecule is going to be nonpolar. So here is my new cleaned up version for you with all of the answers. If you ever need to go back and see, you will be able to see these, no problem. But let's also take a moment to take a look at the ball and stick model from our lovely PhET simulation. So here, I'm going to remove this single bond. I'm going to add a double and add another double here, okay? So as you can see, you can flip it on this particular program to get a better 3D angle, and this one's not 3D because it's just linear. You can click on the geometry, which is going to be the shape, and you can click on the electron part. This one, it says electron geometry. It's talking about the domain here. So molecular geometry is the shape, electron geometry is the domain. And then you can show the bond angle as well, like so. And you can, like I said, rotate, and it flips the bond angle and so forth, like so. And at any time, if you need three-dimensional, reference, this is a very helpful simulation to do that. All right, so back here, looking at the next example. HF. It's a nice, simple, easy one. We only have point A to point B here, the two-atom linear molecule. So let's count how many valence electrons for our hydrogen. One. How many for our fluorine? It's a halogen, so group 17 has 7. We add this up, what do we get? Total of 8. Now there isn't really a central atom here because there's just two atoms. All we can do is attach them together by a single bond so far, so good. That means we have 6 electrons left to do in our structure. So looking here, which particular atom actually needs additional electrons in order to meet the octet? Fluorine. And look, we have 6. And guess how many that the fluorine actually needs? 6. So we draw that in there like so. This would be the Lewis dot structure for hydrogen fluoride. Now, there isn't really a central atom, but the two work together here to create the sigma bond between them. And since it's under the linear domain, what would we determine the sigma bond to be? What kind of hybrid? It'd be an sp, right? So we have one sp sigma bond. All right. What's the bond angle here? Doesn't really change here. It's going to be 180, of course. Now for the polarity, which way does the dipole moment go? Towards fluorine, right? Fluorine's the most electronegative element on the table. That means this side is going to be a partial negative. This side would be a partial positive. So this one is definitely what? Polar. Polar molecule. Definitely polar. Like so. Not too challenging just yet. So what you'll notice under this domain, you'll see stuff that have double and triple bonds in it, which is usually going to be a group 14 central atom. You'll see ones that are 2-atom molecules. And the last example, which happens to be the beryllium compounds. This is the exception here that you have to take note for. Lovely, lovely exception. Beryllium, remember, we're going to remember that only needs 4 in order to meet the octet. So let's go ahead and draw. Got beryllium, how many valence electrons? 2. And our fluorine, 7, but remember we have 2 of them in the molecule, so we need to multiply that by 2. So that's 14. We add this up, how many electrons in this particular Lewis dot diagram? We have 16 valence electrons. Pick out the central atom, shouldn't be too hard. Least electronegative element's going to be beryllium, so that goes in the center, like so. Then we attach our ligands. And since you know beryllium is a special exception and it's under the linear domain, I would always draw it in a linear fashion. So attach your ligands, one on each side. How many electrons have been used? 4, so now we're down to 12, which makes sense because which atom needs additional electrons? Fluorine does, and each one needs how many? 6, so 2 times 6 is 12, which seems reasonable, right? Like so. Very good. Now, let's start with the polarity here. Which way did the dipole moment go? Towards the fluorines, like so, right? We have dipole moment going towards each fluorine. So what happens there to the overall polarity of the molecule? Cancels, so this is going to be nonpolar. Now let's look at obvious bond angle here. Yes, it's still the straight line, so it's going to be 180 degrees. That's going from the F to the BE over here to the F. That creates the bond angle. All right, and last but not least, our type of bonds here and their hybrids and so forth. We have 2 sp sigma bonds. Very simply put, like so. And the cleaned up version here, taking a look at that. And here, if we wanted to use our model to represent this, we could do so here. And as you can see, single bonds, the purple in the middle is representing our beryllium atom, the gray are representing the fluorines. Very simple straight line here in this particular molecule. All right, let's look at the T-planar domain. And I get tired of saying trigonal over and over again. So you can abbreviate T-planar, T-pyramidal, T-bipyramidal, because a lot of them have that trigonal part really telling you that you've got triangles involved. That's that word there. So here, what you should notice, there are going to be 3 electron domains. You have 2 possibilities here. You have 3 bonding and no lone pairs. So this would be 0 lone pairs. That gives you the T-planar shape. You have one other possible option under this domain where you have 2 bonded atoms and 1 lone pair. And that's going to give you a version of bent. So under this domain we have the T-planar and we have the bent shapes. Okay? Like so. And we're going to do a couple examples of each. Before we do that, let's look at the hybrids, because now we have 3 electron domains. So it's going to take 3 orbitals to hybridize. Once again, it's still the same idea. We have our spherical S. We have 2 P's this time, 2 dumbbells, one on, say, the X plane, one on the Y plane. Okay, like so, you have 2 P orbitals. And they're going to do the red and blue make purple idea again, with it being the having a little bit of the larger lobe due to the S, a little bit larger lobes, but there should be 3 of them around the central atom. Here's your central atom. 3 of them that are going to do the bonding around the central atom. So instead of sp hybrids here, we're going to have sp2 hybrids. All right. Let's take a look at formaldehyde. Formaldehyde is CH2O. Let you take a moment to see if you can draw it on your own, follow the rules, and we'll come back in just a minute. All right, just to go back over, because I didn't say this before, the flat triangle is the shape with the bond angles that are going to be ideally around 120. Now, there are a few exceptions here in terms of, as we're going to see with the formaldehyde example, that it's not necessarily going to be exactly 120, but when you're declaring the angle for T-planars, you would say, you know, ideally they're going to be right around 120s. So for drawing formaldehyde here, carbon, how many electrons? 4. We have hydrogen, which is 1, and then there's 2 of them, so multiply that by 2. And then we have oxygen that is 6. Very good. So we add this up, we end up with 12 to work with. Now which atom is going to go in the center? Carbon. Carbon. Remember, hydrogen cannot. And out of the other 2, carbon and oxygen, carbon is less electronegative. So carbon goes in the center. Then I go clockwise. It doesn't really matter though. And I start adding them on by single bonds like so. So you can do it that way, or you know, if you do it where you put the O up here and the H's like this, that's still acceptable. Doesn't really matter. Now, we're not done yet though. How many did I use of my 12? 6. So I have 6 left because I used 6. Now, out of our leftover ligands here are hydrogens and oxygen. Which one still needs electrons? Oxygen. So we're going to use those 6 to satisfy the octet of the oxygen. But that puts us at 0. There is a problem. What's the problem? Carbon is not have its 8. It only has 2, 4, 6. Okay? So this means we have to take off a lone pair and create a double bond in order to make it have everybody has 8 or the hydrogens have their 2. So doesn't really matter if you draw, like I said, on which side you put them. Like this one over here would be fine if you did the same thing and you made this a double bond and put the lone pairs on the oxygen. It still would be acceptable. Now, looking here, we have a couple bond angles. We have H to C to H, this bond angle right here. What is that going to be, approximately? 120, right? Because this is the flat triangle, right? And we're talking 360 degrees, and if we have a third of them, a third of 360 are going to be 120s, right? Also, let's look at the bonds. We have 1, 2, 3 sigma bonds, but what type are they? So we have 3 sp2 sigma bonds. Okay? And what else do we have? This one right here, the other one of the double, that's going to be 1 pi bond. Like so. Now for polarity. Dipole moments. Where does the dipole moment point? Towards the oxygen. So it's going to go this way. I do want to point out to you as well, though, so that you know this for future and for all organic compounds that have C to H's in there, the hydrocarbon bond. C to H has an electronegativity difference of 0.4. So the C to H bonds are always considered nonpolar covalent. So the only polarity here is really like the oxygen pulling. So this side of the molecule is going to be the slight negative. This side over here by the hydrogens are going to be slightly positive. So in terms of polarity, this one is going to be polar. Okay, this is going to be a polar molecule, like so. Okay, so let's look at the cleaned up version, and then we're going to try the ball and stick model. Before we do that, though, I just want to point out that we say ideal bond angle of 120 because if it does have a double bond or a triple, well, it won't have a triple bond and be under T-planar, but if it has a double bond, that is a slightly bigger domain of electron density here. So the angles, although they're still very close to 120, as you can see, it pushes the chlorines, or if you were looking at the previous structure, the hydrogens would be a little bit closer together because this particular area takes up a little bit more space. But they're not going to ask you for actual bond angles here. They would just say, what is the ideal bond angle? And because you know it's T-planar, it's a flat triangle, you would say 120s. Okay? All right, so here, looking at the ball and stick model, we'll add on our double bond here. So as you can see, here it gives you the ideal bond angles for this particular molecule, and this is under, the shape is trigonal planar, the domain is trigonal planar. Let's take a look and see if we have any under here, though, that might fit this. I don't see, let's see here. Nope, nope, nope. Okay, so there isn't one under the reel that's going to fit that situation. So, and as you can see, I rotate this. As you can see, it's very much flat triangle. Okay? Really is just only on the one plane. All right, so definitely try to visualize 3D, that spacing, and so forth. So here's the cleaned up version. We do have the dipole moment that goes towards the oxygen. We do have the 3 sp2 sigma bonds and the 1 pi bond. And the ideal bond angles are going to be 120. The second trigonal planar example here has to do with boron. And like beryllium, boron does not follow the octet rule. So if you look down below on your Lewis dot rules sheet, it shows you another thing to remember is that boron only needs 6 valence electrons in order to satisfy the octet. So this one's a little bit easier than the formaldehyde, you'll see. Let's go ahead and add up our electrons. Boron gives us how many for the structure? 3. And the chlorines bring in 7 each, and there's 3 of them, so that's going to be 21. So that's a total of 24 valence electrons to work with. Central atom. What's the central atom? It's going to be boron. And we attach our ligands, so attach the chlorines, like so. How many of the 24 did I use? 6, so now we're down to 18. And how many does each chlorine actually need? 6, so 3 times 6 gives us the 18. So that's going to go to 0. All right. All single bonded here. Nice easy structure. The only little glitch is that boron does not follow the octet rule. And 6 valence electrons will satisfy the octet. Now looking here, so what is our type of bonds that we have around our boron, our hybridization? 3 sp2 sigma bonds. Very simple. What are our bond angles? 120 for the flat triangle. And let's draw in our dipole moments and figure out polarity. Which way do the dipole moments go? Towards the chlorines, right? So what happens here? They cancel, and this structure is going to be non-polar. Very simply put. So bond angle 120, 3 sp2 sigma bonds, and it's nonpolar because they cancel. Real quick, let's take a look here at our triangle. The only thing different from formaldehyde is, yes, we take off the double, we put on a single, but as you can see, Still a flat triangle with 120-degree angles.